Now let's talk about stochastic methods and stochastic modeling. In case of stochastic modeling, we are constructing a set of the different models, while in deterministic methods, we are counting only a single model. What's the difference? Imagine that you get two wells. You get values in these wells, for example, porosity. And what do we know about the interval space? We can apply a certain interpolation function, a kind of deterministic function, either spline or Kriging, and we're going to obtain something between them. But still we are not sure that it looks just as we draw. But what we can do is we can draw a different possibilities, a different realizations of the shape of the function between the wells. And that gives us stochastic modeling. Let's look at the example. Here we got 4 wells with a certain values of well tops, and we did Kriging. As you can see, outside of the range, Kriging gives us the average value. But you can see that in this big interval, it's only average. But it looks not logical, it looks not geological, because you see that our values are changing. It has to change all around our investigated area. In geology, we are not applying these flat surfaces. So this one looks not real. But how it should look more real? Our model should represent the variability, the changing of our initial data set. And it should look like more or less as it's shown on a figure. But the problem is that the example shown on that figure is not the unique. We can draw a different realizations, and each of these realizations going to be equally probable. And that gives us stochastic modeling. Let's find how sequential Gaussian stochastic simulation is working. Imagine that we got this grid with the 4 wells and porosity between 10 and 20. Sequential Gaussian stochastic simulation is geostatistical interpolation function, stochastic, and that keeps variation. That is interpolation function, that means we're going to find the values between the wells. It's geostatistical, that means it's based on the variogram. It's stochastic, that means it's going to give us a different realizations. And it's going to keep the variation. Let's look at the example how it works. First of all, we need to have the set of variogram. So we need to know what's the variogram range. In addition to that, we need to have the distribution. So the values between the minimum and the maximum. And in our case, it should be Gaussian distribution or the normal distribution. Once we run the process, it randomly chooses a certain point in our dataset. For example, it takes the bottom left one cell. This cell is outside of the range of all of our wells. That means the point is independent. That means program can randomly choose any type of the value for this point. And in our case, for example, it gives us 11. That is possible value. We run the program once again, and then it randomly chooses this highlighted cell. What's the value in this cell? Actually, in this cell, our value should be somewhere between 18 and 12, because this cell is located nearby to these two values. That simply means that we cannot put here 11 or we cannot put here 20, because this cell is influenced by the nearby cells. So we can put here, for example, 16. And we're going to run the process once again till we fill all of the cells. The important thing to mention here is that each previously calculated cell on the next step is accounted as the new well. What does it mean? If you can see on the bottom part near the well, near the point with porosity of 11, we get values that are equal or nearly equal to 11. It is 12, 14. But why these values are looking like that? Because on the first run, randomly, computer chooses this point and it gives it a small value. It could happen separately, it could happen differently, but it gives us the small value at this point. So what we can do is we can run the algorithm once again, and it's going to give us different solution. For example, like that. You see, once we run the algorithm once again, it gives us different values in the bottom part. Now it gives us 16 and 17 porosities. That means that in this place our porosity is higher than in the previous case. But why it can be higher or lower? Just because it's outside of the range and we don't know the actual values here. So that's why for each realization we choose the different values. That is the main difference between kriging and the sequential Gaussian stochastic simulation. Because in case of the kriging outside of the range, we simply take the average. But in case of the stochastic simulation, we try to keep variation. We try to follow the changes in our dataset. Let's look at the example of our sequential Gaussian stochastic simulation. These three porosity cubes was calculated using the same parameters. Nearly zero nugget, type of the variogram spherical, anisotropy range 1,500 in both directions. And we can see that these three porosity cubes looks similar but not the same. And we can see that in the central part we get the area with a low porosity. And that is happening because we have some wells inside this area. And because of these wells, this area gonna always keep small values. But in other places of our model, value can be either high or low, depending on the distance between the wells. Outside of the range, the values are independent, so in one case it can get the real high values, while in another one it can get really low values. How we can apply sequential Gaussian stochastic simulation? We can apply it to obtain a different realizations of porosity cube. And then out of these different realizations, we can find the best one, the one which is better represents our initial data set. But how to find these parameters? How to find the nugget effect, type of the variogram, and anisotropy range? Just as we did that in the variogram analysis part, we need to calculate three variograms: the vertical one, the major direction, and the minor direction.